Our goal is to calculate the equilibrium constant K for this reaction, so for this reaction right here. And we're going to use the standard reduction potentials to do so. So in the previous video, we talked about the relationship between the equilibrium constant K and the standard cell potential, so E0. So if we can find E0 for this reaction, we can calculate the equilibrium constant K. And we've seen how to find E0, the standard cell potential, in earlier videos. So let's start with this first half reaction here, where we see solid iodine gaining electrons, so it's being reduced to turn into iodide anions. The standard reduction potential for this half reaction is positive 0.54 volts. And we can see that's what's happening in our redox reaction up here, right? We can see that we're going from solid iodine on the left side, and we have iodide anions on the right side. So we're going to keep this reduction half reaction. If we look at what's happening with aluminum, we're going from solid aluminum to aluminum 3+. So solid aluminum must be losing electrons to turn into aluminum 3+. So aluminum is being oxidized here. But this half reaction is written as a reduction half reaction. So we need to reverse it, right? We need to start with solid aluminum. So we reverse our half reaction to start with solid aluminum. So aluminum turns into aluminum 3+, and to do that, it loses 3 electrons, right? So loss of electrons is oxidation. Here is our oxidation half reaction. So we reversed our half reaction. Right, and remember what we do to the standard reduction potential. We just change the sign. Right, so for the reduction half reaction, the standard reduction potential is negative 1.66. We've reversed the reaction, so we need to change the sign. So the standard oxidation potential is positive 1.66 volts. For our reduction half reaction, we left it how it was written, right? So we're just going to write our standard reduction potential is positive 0.54 volts. Next, we need to look at our balanced equation, right? We need to make the number of electrons equal for our half reactions. So for this first half reaction, I'm just going to draw a line through. This half reaction, so we don't get ourselves confused. For our first half reaction here, we have 2 electrons, and then over here, right, for our oxidation half reaction, we have 3 electrons. We need to have the same number of electrons, so we need to have 6 electrons for both half reactions. Because remember, the electrons that are lost are the same electrons that are gained. So we need to multiply our first half reaction by 3. Right? If we multiply our first half reaction by 3, we'll end up with 6 electrons. And our second half reaction, we would need to multiply the oxidation half reaction by 2 in order to end up with 6 electrons. So let's rewrite our half reactions. So first we'll do the reduction half reaction. So we have, let me change colors again here. Let's do this color. So we have 3 3i2 now, so we have 3i2, and 3 times 2 gives us 6 electrons, so 3i2 plus 6 electrons, and then 3 times 2, right, gives us 6i minus. All right, so we multiplied our half reaction by 3, but remember, we don't multiply the voltage by 3 because voltage is an intensive property. So the standard reduction potential is still positive 0.54 volts. So we have positive 0.54 volts for this half reaction. Next, we need to multiply our oxidation half reaction by 2. So we have 2Al, so this is our oxidation half reaction, so 2Al, so 2 aluminum. And then we'd have 2Al3+, so 2Al3+. And then 2 times 3 gives us 6 electrons. So now we have our 6 electrons. And once again, we do not multiply our standard oxidation potential by 2, so we leave that. So the standard oxidation potential is still positive 1.66 volts. Next, we add our 2 half reactions together. And if we did everything right, we should get back our overall equation. So our overall equation here, we have 6 electrons on the reactant side, 6 electrons on the product side, so the electrons cancel out. And so we have for our reactants 3I2, so we have 3I2 plus 2Al. And for our products, right here, we have 6I minus, so 6I minus plus 2Al3 plus 2Al3 plus. So this should be our overall reaction, right? This should be the overall reaction that we were given in our problems. Let's double check that real fast. So 3I2 plus 2Al, right? So right up here, so 3I2 plus 2Al should give us 6I minus plus 2Al3 plus. So 6I minus plus 2Al3 plus. So we got back our original reaction. Remember, our goal was to find the standard cell potential E0, because from E0 we can calculate the equilibrium constant K. So we know how to do that, again from an earlier video. To find the standard cell potential, right? So to find the standard cell potential, all we have to do is add our standard reduction potential and our standard oxidation potential. So if we add our standard reduction potential and our standard oxidation potential, we'll get the standard cell potential. So that would be positive 0.54 volts, so positive 0.54 plus 1.66 plus positive 1.66 volts. So the standard potential for the cell, so E0 cell, was equal to 0.54 plus 1.66, which is equal to 2.20 volts. All right, now that we've found the standard cell potential, we can calculate the equilibrium constant. So we can use one of the equations we talked about in the last video that relates the standard cell potential to the equilibrium constant. So I'm going to choose one of those forms. So E0 is equal to 0.0592 volts over N times log of the equilibrium constant. So again, this is from the previous video. So the standard cell potential is 2.20 volts, so we're going to plug that in. We're going to plug that in over here. All right, so now we have 2.20 volts is equal to 0.0592 volts over N. Remember what N is. N is the number of moles transferred in our redox reactions. So we go back up here and we look at our half reactions and how many moles of electrons were transferred. Well, 6 electrons were lost, right? And then 6 electrons were gained. So N is equal to 6. So we plug in N is equal to 6 into our equation. So N is equal to 6. And now we have the log of the equilibrium constant K, log of the equilibrium constant K. So we just need to solve for K now. So let's get out the calculator and solve for K. So we would have 2.20 times 6, right, divided by 0.0592. And that gives us, let's say, 223. So this gives us 223. So 223 is equal to, so this is equal to log of our equilibrium constant K. So we need to get rid of our log, and we can do that by taking 10 to both sides, right? So if we take 10 to the 223 and 10 to the log of K, then that gives us K, the equilibrium constant. So K, the equilibrium constant, is equal to 10 to the 223rd power, which is obviously a huge number. So a huge number, we get a huge value for the equilibrium constant, which is a little bit surprising because we only had 2.20 volts, right? Which doesn't sound like that much. So from only 2.20 volts, we get a huge number for the equilibrium constant. So the reaction goes to completion, right? With a huge value for the equilibrium constant like that, you pretty much don't have anything for your reverse reaction, which is why we're not drawing any kind of arrow going backwards here. Right? We only have this arrow here going forwards. So because of our huge number for the equilibrium constant.